Well, thank y'all for inviting me here. I'm going to get to talk about my favorite thing, which is aquatic systems. Specifically, I'm very fond of fish, as well as about anything that can crawl. One of the things that I think is wonderful for kids is that water is very special in that you can go down to the beach, walk into the waves, and you're in a different world. And I always thought that was fascinating because you look back at the beach and there's all these people there. You turn around and look out and there's nobody there. You get little goggles, you go out and, it's like, wow, this is like the undersea world of Jacques Cousteau. Some of the older people may remember that. And anyway, so I just think it's a wonderful way of kids get connected back to nature, that are and learning a lot of things because just about everywhere you turn, there's something you can learn about the natural system. Well, I'm going to talk a little bit about water and why is it so important first. Of course, we live on a blue planet. And it's very obvious when you look at it. It's mostly ocean, or water, not land. And so it doesn't make any sense not to learn about it in terms of it affects everything: the weather, currents, temperature, you name it. And so and it's an intricate web of interconnections, physical and biological. And of course, there's we have NASA in this area, and people are always wanting to know about potential for extraterrestrial life. And there's a quote from Sylvia Earle, very famous oceanographer. There's plenty of water in the universe without life, but nowhere is there life without water. And that's so true. And there's properties of water that make it very unique. That's why it's used in so many religious rituals, various religions, blessings, cleansing, and so forth, because it has these really amazing properties. One of those is it comes in different forms. It exists in all three forms in natural environment: solid, liquid, and gas. But one is very interesting is that, I think I'll show it here in a second, is the physical properties of water give it some very interesting attributes that you don't find in any other common substance or any other substance at all. And without it, life wouldn't exist. And that is, it's a solvent. It supports, chemical reactions. And one of the biggest ones that I always thought about, and it's very subtle, unless you read Kurt Vonnegut novels, you may not have ever heard of it. But I'll get it to you here in a second. And we're going to talk a little bit about the water cycle and how it helps connect us to the rest of the watershed, rest of the continent. And we, right here at the coast, we're very fortunate because we get the effect of inland and coastal processes. And you can see, I had another presentation I gave a few years back where we followed, where the water drop would go. If we dropped it over back in Dallas, it would end up some here in the Gulf of Mexico one time. And you could actually trace the pathway it's taken. And things that happen in the watershed, therefore, are going to affect everything all the way down to the Gulf of Mexico. What we have here on this slide, if you can see it, are all the major processes where water comes from. Because I always thought, where in the hell did water come from? Just here, did it come with the big, flood with Noah or whatever? And it comes from various locations, but once it gets here, and it cycles back and forth because the solar energy drives it. And you have water through the process of the condensation, forming water particles, drops, and rains down in the form of precipitation, rain if it's liquid, snow if it isn't. If it's snow, we have the extra benefit of having it in a form that we can store it and predict how much we're going to have for the rest of the year when it starts melting like they do in California. Here we have reservoirs. We don't have any big supplies of snow or ice. And then, of course, if something disappears, that becomes part of the groundwater supply. And of course, that's places like up in Austin, that's very important because that water eventually recharges those aquifers. And if it gets contaminated, and you may have seen this when you go up to Austin, they have protection zones for groundwater where you got to be very careful. You don't want to spill no gasoline because it only takes a little bit of gas to contaminate a large area. And so ultimately, some of it flows underground, some of it flows on the surface and makes its way back to the ocean, in which the cycle starts again. Here in the Gulf of Mexico, we got currents mostly at the surface because we have a shallow sea. But in some places like California, the West Coast, you have very deep water And so a lot of this sinks down, or it gets caught on some of these gyres, because when the Earth is rotating, you have a gyre that creates, and so water is displaced to the right at a certain angle. And so it starts moving things away from the shoreline. If it moves enough, it brings water from the bottom, and that's upwelling. Okay? And so all these factors interact with each other. It's a very complex system, but people have done a pretty good job of mapping the flow of water. And so in the cases of rivers, which a lot of people, of course, live near, the one factor that's very important in regards to water is just how much water is flowing past a point at a certain time. And we measure that in a volumetric way, looking at like cubic feet per second, or liters per second, or millions of gallons per hour. And so we get an idea of how much is passing a certain point. And you think, why do you want to do that? Well, one, you might want to divert some of that water for irrigation. And somebody may have a water right. Here in Texas, in a lot of states, you can have water rights. And that means that if there's water in the river, you can take it out, or if it's groundwater, that's managed differently. And the stuff that's left over, people can use. But if they're the junior water right holder, because they came in late, they can't use it unless everybody else is happy with what they got. And so what flow has been considered what they call the master variable, because it affects everything else. Moving water transports a tremendous amount of sediment. It can erode banks, and it can destroy them. And some fish and invertebrates prefer fast-moving water that's clear. At the upper ends of the watershed, you have streams that flow very fast, and they pick up, only thing they can really transport is heavy particles, and very well, and that's why the stream looks clear. As it slows down, it can't carry those heavy particles, and it starts dropping out. First the larger ones, and then bigger ones, and so you have lots of little sandbars that develop. But the changes in flow is associated with changes in water temperature, dissolved oxygen, type of habitat. When I worked on the West Coast, one of the things we looked at is flow. And so at this level, if you imagine this room full of water, and you could stand on these things here, you got one spot that's high enough to keep you out of the water. Okay, maybe a table or two. And as it goes down, you got more and more dry area. And so biologists started noticing that some fish do quite well at different conditions. When the water's really high, they like to get up in the brush. They'll swim out there and get out of the way. You see that a lot with salmon and trout, because they like to rest. They move over to the side. They don't want to be in the middle of the channel because they got to swim really hard. And so they'll move up, get underneath a rock or boulder. And so that you can map that and see how, using GIS or kind of a CAD program, you can see how that changes with flow. When it gets deeper, you got a different scenario out there. And so that's become a very big thing in terms of science, predicting where the animals are going to live and what kind of habitat they're going to have. Other things you can cue in on is the channel shape, because if you have a very narrow, deep channel, the water tends to just go straight through it really fast, like we have here in our urban streams. Okay, so anyway, water doesn't flow at the same time, the same speed in same amount at all the time. It changes and varies. And here in the States, and as well as other countries, we have devices we can measure how much water is flowing past the point. And it's measured typically here in the States, because we're in the United States. We don't use a metric system. We do it in feet per second. And so we have a device. We go out to the channel here, and you can get a pole, and you have a little propeller, and it spins around. And pretty simple to use. Now they got acoustics and electronic stuff. But I like the old-fashioned one because you can see if it's turning or not. You hold it there, point it to the current coming out from upstream, and you count the number of clicks, and you have conversion formulas. You can change it to feet per second. And so you take a measurement, and let's just say, it gives you the velocity. Say you're in the middle of the stream, but you want to know not just how fast the water is moving, you know how much water is going through there. And so you go across the stream, lay a line, you know how wide the stream is, so you have length or width, and then you measure number of feet per second times feet, that's cubic feet per second. So cubic feet per second can turn into gallons per minute, convert that. And so you can measure the profile for the whole thing. Now they have, like I said, they have acoustic devices now that are very sophisticated, and they're nice, but the difference between one of these little poles and one of those gadgets is like several $1,000s. But that one will map it three-dimensionally, and you get a nice little graph. And you can see not only how much water is coming through here, but where's the water moving the fastest? Because some fish need fast-moving water. Here in Texas, those are things like typically some minnows, darters, which are very colorful, and they like fast-moving streams, so they stay in cobble and stuff like that. Whereas if catfish, or bass will like to move in pools because they have lots of cover and they can ambush ambush predators. And so, but here is a hydrograph, and when we got these gauges that USGS or the state puts out, they measure the height. Okay, and so you say, wait a minute, I thought you were measuring speed. No, they measure the height of the water. And what they do is when the USGS does this, and they do it every 3 or 4 years, they'll go out there and they'll measure the height, and they're measuring flow right then with one of those fancier devices. So when they come back out, all they got to do measure is the height. And if the channel hasn't changed, they say height equals this flow. And so they can do that remotely, using a computer. And so that's how they get the estimates. And they convert it to flow, and that way they can tell people. And they can also convert it to height, which people who are worried about flooding care about that more than just the flow. Okay, so these little arrows here point to different functions of the watershed. Floodplain, that means the water gets that high, it's overflowing the banks. You say, well, what's good for that? Well, that's good because it helps stabilize riparian vegetation. It drops out the mud. And some fish, like gars, they spawn in these deep water pools. When the water gets high enough and it goes over the banks, then you have these oxbow lakes. You've probably seen them, like over the Brazos River has a lot of them. And the young, they lay their eggs, and all the young gar, like alligator gar, spotted gar, they'll grow up in these little ponds protected from predators. And then when you have another flood next year, the water connects to the main river, and they all swim out there, and they're bigger now. They can grow and get bigger. And so then you also have water quality, because you don't want to, if you cut the water too low, you don't have enough aeration, so it might get really low oxygen. And then you see here, it shows red lines. They're calling that minimum flow. And then they have these darker lines that says functional floodplain flow. They can calculate at what velocity does it activate the movement of sediment. And every once in a while you get a very big flood, and that's when it changes the whole shape of the river. And that's, they've calculated these numbers where in like 2 days, the majority of the river has moved in terms of dirt, soil, sediment, and so forth. So it's quite an amazing effect. And then it shows other things here that might be for spawning seasons, different times of year, to support fish, macroinvertebrates, and amphibians. And so all these functions the river does that for us. We don't have to pay the river to do that. We don't have to design engineering systems doing it naturally. Why? Because all these organisms evolved in these systems, and they've timed their life history traits with it. When they spawn, because when they spawn, they let go of eggs. The eggs need to get transported somewhere. And so they usually spawn when the water's rising, and or when they're migrating. They might, have a little push might help them.
So they spawn in the water rising?
Well, not all of them do. Some, yeah, but that's in the springtime. Here is when we have a lot of spawning activity here in the rivers. Some of them, like bass and bluegill, different centrarchids, they like to spawn in little pools and pond, off channel stuff. A lot of structure.
When they so if you have one of those big floods that basically re-engineers the morphology of the stream, does that when they go out, and do they then go out and redo the measurement of height versus?
Yeah, that's when they need to do it, because the whole relationship has changed now. Yeah, so they're, I don't know how often they do it, if they have a certain formula, but I'm sure they do. Like when it gets, so much of a flow, if you have an event like that, then you need to redo your calibration curve, or they call it rating curve. And again, they're not doing, what they do now is once they put the staff down, they have an automatic thing that, tells you how high the water is. And then they plug that into a formula. Now they got, like I said, this stuff, like a lot of technology, is changing very quickly. They also have things they can mount underneath bridges. They're pinging, sending sonar sounds from the bridge, and they know that distance is equal to a certain depth in the water. And so they do that, and it automatically corrects itself.
And they're just using the density difference to tell.
Yeah.
Oh, that's cool.
They're bouncing the signal off the water surface, and so they know, they still got to check the channel morphology. Okay, so why is this important? Well, this, moving water is power. And if you've never experienced that, just hang out around when it's flooding. You'll pick up cars and move it along. And when I worked in California, we worked with salmon and fish like that. And we had to put these little meters into the rock. And so we actually had these underwater pneumatic guns that would drill into the brick, and we had this epoxy. And so we would put the brace that holds the device in. It's like a little cylinder. And when we put the tags on the fish, as they're swimming by, they'll ping, as they're passing by. That tells us something just came by. And we have the number of the fish and all that kind of stuff. Well, anyway, there, because we have these almost V-shaped gorges that go up, 100 feet, when you have a big flood, all of a sudden it's like, woo, and you come back, say, where's our thing? They said this boulder about almost the size of the room here in terms of height, it's gone. And it's like amazing. And so it's rolled down a little bit further. And, you just wonder what kind of force we have to move that gigantic object. Well, when you have that little bit of water pushing every little surface area that you're looking at, it doesn't take much to move a car or move a boulder. And so that force is rechanging the channel morphology. And so anyway, we lost one time, and we were able to find it because we had a little flag, and then we also were able to talk to it. It had like a radio thing on it. And so we were able to find it, but it was like 100 feet downstream in this gorge area. And big old boulder. And fortunately, it was mounted like on the side. So when it started turning, it was just turning like the axle. And instead of like, it could have turned this way and it would have smashed it. It was so big. And so anyway, the other thing is, if you have a lot of power, say the slope of the stream, that's what this little diagram is trying to show you, the interrelationship, and it shows flat and steep. So if you have a steep relationship, that's going to make, it's going to have more stream slope, and so the water is going to discharge faster because it's running off real quick. And so what will happen there is you'll have, either aggradation or degradation. Aggradation is deposits of sediment. Degradation is where it's being scoured out. And so that's very important if you want to build something there. You don't want to put it in a place that's going to be scoured out in a few years. Now also the types of sediment, as I mentioned, when you have fast-moving sediment, you can carry bigger pebbles, okay? And if you look at the stream, you'll see, as it's curving out this way, you see a deposition of big, stuff, because it slows down, on the inside turn. As you're on the outside, it speeds up the water. So it can carry bigger objects. And so on the end, over here, it's moving out because it's dropping off all the smaller stuff. And the fish, you have some fish that like that coarse sediment, some that like real silty sediment. And so they tend to sort themselves out by the habitat type. Sediment supply, water, we interact with each other. A lot of water, a lot of power. You'll be able to carry lots of things. Okay, so, but in addition to this natural processes, we also have things happening in the watershed that can really change things up. And here is showing an area that what might happen if we have a climate change scenario. Normally, as you start to urbanize an area, you have more impermeable surface. So it rains, the water it goes off really fast. What would you think happens in the adjoining stream? Does it start rising slower? Does it rise fast? And so we have our flash floods because things run off so quick and then they fill up the stream and all of a sudden, boom, it's really high. The thing with that is that, again, everything's interrelated. We have climate change, and that's associated with growing, fossil fuel emissions, and we got more urban areas, industrial areas. It gets hotter. You got more impervious areas, so when it rains, it heats up faster. It runs off quicker, and so you end up in areas that are urbanized, also having all these other problems associated with the changing climate. And it's tough on fish. I mean, I've been out here on the east side of town, and streams that, you walk out there, it's like, it feels like you're in a hot tub. I mean, in the summer. I mean, it's like super hot, and it's like, holy cow, how do these fish live in here? Well, they've adapted to these urban environments. To them, they just think it's a big boulder field, I guess. Anyway, but you're going to see one of the predictions we have, is everybody worries about getting hotter, and certainly that's an issue, but it's not so much that that's the issue. To me, the real issue is things are getting more variable. And previous investigations showing climate, it wasn't that, oh man, it got so cold we had the ice age and everything went to hell. No, we weren't stable very long. So they start growing grapes, and then it gets too cold, and they start to switch to wheat, and then flip-flop, for thousands of years until finally the climate variation settled down. It wasn't so variable. Well, when you have that variability, these organisms, they've evolved for a certain regime. If all of a sudden you change it quickly because of climate change or urbanization, dams, that's another big one. People build dams, and we fragment the natural river corridor. So things that need to spawn, they can't move upstream or downstream. Now, there's an art and a science to measuring these processes. Now that we have this wonderful GIS system, you can use that and couple it with models, and you can predict what will happen if we increase the discharge at a certain amount. And you can see where it speeds up the water. You can look at sub areas. And so we talk about a watershed. What is that? Well, you have a line at the highest elevation that separates, if we drop a water here, one of them goes to the Pacific, the other one goes to Mississippi, theoretically, somewhere in Colorado, or any other smaller watershed. Things, of course, on one side are going to be infecting other parts of the watershed, and the land use there is not going to affect the land use on the other side because the water is going to run that way. Now, one thing, too, that I learned many years ago, I'm not no geologist, but I thought it was fascinating. I took a class up in Oklahoma, and there's this really famous geologist at that time, and he showed us how on the back of an envelope figure out where's the groundwater going, because it's connected to the surface water. And it's, again, I would not conduct a big study with these methods, but I just thought it was fascinating. And of course, this guy was like, hardcore geologist. In his house, inside the house, he opened up a little canopy, and there's a groundwater well there. So he could record what the groundwater is doing in his neighborhood. And whenever the trains came by and parked their trains there, you could see that the depression in the cone of the water level, it would sink. And the same with trees. He had some sensors all over the place. I thought, man, that's cool. But anyway, they're all interconnected. Water, it travels freely between a lot of these groundwater sources and surface water. Not always. We can also look at a budget for a particular watershed. If, say, you're a city planner or somebody that needs to deal with flooding and water supply, you can measure these using a variety of techniques. Some are pretty straightforward, some of them a little bit more complicated. And look at the amount of water coming in out of the system being the watershed you're interested in, and how much is going out. And is that sufficient to meet all the environmental needs as well as human health needs, and wastewater, drinking water, and so forth. Again, this has become a lot easier now that we have really nice GIS systems. Here's a example showing how much between areas water temperature and mean flow has changed, and that's mean average river flow. And so in areas where you've been having increasing temperatures, you notice that the large areas are becoming having more low flow conditions, and so that means they're probably not sustaining themselves because it's evaporating away, or it's being overused for irrigation or for animal agriculture. During low flow periods is when you typically find a lot of stressful conditions because it's warmer, it's not mechanically being aerated, so oxygen perfusion is not as good as it could be, and so it takes a little bit of waste and it can get very anoxic very quickly. In climate change, we know that in some areas it's going to make it drier, but we don't know exactly because what's going to happen to every single little spot in the country, because most of the climate models are based at a large scale, and they talk about downscaling to your area. And the National Weather Service has been trying to do that for the last 10 years or so, taking those big forecasts and say the South or the United States is going to get drier. Yeah, but not everywhere, not evenly. In some areas it may get wetter. And so kind of downscaling their model to try to find these areas. depends on having good information for the environmental conditions that occur there already. Anyway, they can also manage that by instigating ways to reduce the amount of water use and also to promote biodiversity. And it shows here hydrological parameters like dissolved oxygen is a good one, temperature, pH, and also the numbers of certain benthic organisms like the EPT index from Lepidoptera and Trichoptera, and different fish species that are known to be sensitive to changes in flow or oxygen. There's other things though besides that. Some of them have nothing to do particularly with the stream, have more to do with the activity of human beings. We also have chemical spills, and that can happen anywhere at any time. Have a car or truck or railroad go off this bank and boom, you lose miles and miles of river. One of my first jobs out of college was investigating fish kills for Parks and Wildlife. And I saw all kinds of crazy things. I saw one time we had a massive explosion east of town over there by Pasadena. And the same day, the very same day, they had a bunch of these gas lines blowing up over there by Sugarland. And all the news media just swarmed that area because, it's fires, explosions, it's loud. Everybody's like, oh, look at this. It's horrible. At the very same time, very same day, we had the biggest chemical spill in the country occur on the ship channel. And what happened was there's a mobile mining which extracts phosphorus from different types of substrate using acid. Their levee breached, and I don't know how many millions of gallons of water went into the ship channel. They had to shut it down for like 3 or 4 days because the pH dropped below 2. Can you imagine ambient water? You never saw the fish. They never came up. And this is an area we know there's a lot because we had a monitoring program going on, and we got thousands and thousands of shrimp, crabs, or whatever. So anyway, if you have a lot more of that activity because the world's getting warm, the reaction rates of these chemicals are going to accelerate. Because most of mobile mining. Yeah, you can look it up. I said out you're going to get a lot of information because hardly no one knew about it. I think Deer Park news media showed up and that was it. And it's all because that other thing was going on, and it was boom, boom, spectacular like a big fireworks show. And there was some gas tanks and everything blowing up. And I always remember that because I always tell the students about that. It says, be careful what you think is going on in the environment because the stuff that we get through the media, through no fault of their own, it's just the nature of the beast. Fog of war, whatever. You got to wait for things to develop. And people run around with heads chopped off and you're trying to figure out what's happening. And you walk in there and you say, oh, this happened. No, we'll find out eventually what will happen. And not saying anything bad, it's just that there's too many moving parts. But that was, that really took it. And nobody even said anything. I remember, so when I see something on the news now, I say, I wonder what really happened. Okay, so an urban stream, again, one of the things that happens is you start affecting the rate of water runoff. And if it runs off too quickly, that's a lot of water moving very quickly. It can erode things, and it's very powerful. The power of that is amazing. We want to try to see how that affects the biota there because certain organisms can't live in an eroding bank environment. Like if you have a crayfish or you have these invasive fish, they're called Plecostomus or armor catfish, they dig holes in the bank. And that's not going to cause a problem by itself, but when water starts moving very quickly, instead of a solid bank, you have a honeycomb bank, that stuff's going to start falling into the water and erode quickly. So a lot of efforts has been put into trying to understand the effect of hydrology, habitat alteration, and ecological condition, and the type of habitats needed to maintain that. You got to have an understanding of how those all interact. A lot of expertise needed. You need hydrologists, you need biologists, you need meteorologists, you need soil scientists, you need wetland scientists to really characterize what's happening in that stream or water body, anything. There's great opportunities for younger students as far as a career. There's usually something they can find. Anyway, we go out and collect stuff on terms of the flow. We measure it. We go and see what fish are out there or invertebrates. And we have sites scattered around to characterize that entire watershed, maybe before downstream of where they come together. And then we map that out and we can develop relationships between the diversity of organisms or some water quality variable and the flow rate. And you can, calibrate it toward the type of land use. And here we have multiple stressors. That's even makes it harder because if you see a decline in fish or caddisflies or whatever that you're interested in, vegetation, riparian vegetation, there could be a lot of things happening in a watershed. So there used to be a phrase where know your watershed. And knowing your watershed meant you got to go out there and see what's actually stressing your stream out. And that can be things like changes in their anatomy, changes in diversity. And the other thing you got to realize is there's a lag time once you hit a big peak. And so you got to wait and see, where am I at? I mean, has this started raining? And if it did, the whole effect hasn't occurred yet. And what it does is what happens to that water? It percolates down into groundwater. Some of it runs off, some of it's absorbed by roots. And you have these various symptoms you can observe if you're looking at an urbanized stream that has lots of built environment. And so these are all really interesting here. There's a whole system that's been developed to address and look at stream morphology. And why is that important? Because again, it starts affecting the physical habitat of the animals. In freshwater streams, you have spills, improperly treated wastewater, septic tanks, urbanization going on. And you typically find large sources of bacteria, indicator bacteria, that suggests that there might be some sewage flowing in the stream. Coastal systems are a little bit different. And why is that? Because salt water, the water goes upstream and it goes downstream. And so it's a little bit more harder to characterize conditions there. But they're still very important because a lot of stuff happens in the coastal water bodies, because everything flows downstream, and so they get the brunt of everything that's been in the upper watershed. And you might be regulating flows because you're taking some water for irrigation. Now here in Texas, you also have the other issues, not just Texas, everywhere, of natural climate gradients. You go from East Texas to West Texas, you got naturally less water and rainfall, less runoff, and guess what? Look at the salinity of these bays. You got seagrass down in South Texas, you got oyster reefs out here. And people always say, well, if we take too much water away, that's bad. I said, there's no bad or good, it is. You'll get in another equilibrium stage where these types of organisms will only live if you starve them for fresh water. And so a lot of efforts have been done here in Texas. They had a program a few years ago called Senate Bill 3, where every watershed had to get studied, and the state gave a lot of money, and the river authorities did too. And so what we have here is a complex system because it's the density of salt water is stronger than fresh water. And so we put equal, and don't mix it too much, just pour some salt water, maybe you can put some dye in it. This is a very easy exercise for students. And then you pour it into fresh water, and they'll stay separated unless you just like shake them together. Years ago, I had a big giant saltwater tank, and I went to bed and I forgot to go check the water hose. I was filling it out, and I had some very expensive fish. Went back to my dining room, and there's the tank with all the fish like way at the bottom, and because they were trying to stay with the salt water, and the water's just pouring out of the tank. But I didn't lose a single one. But it just shows you they know that's salt water. They know where they need to go. And so in an estuary, you got a mixture of those. You tend to have, as a result, partitioning of the estuary among different types of organisms, like freshwater fish and organisms, river prawns, versus saltwater shrimp, crabs, and so forth. This is kind of a classical pattern here. And we also have a certain life cycle that you find in marine estuarine organisms. That is where they spawn offshore, lay their eggs, and then with tidal transport, they're pushed back into the estuary. And how they do that, people always wondered, well, they go up and down the water column. When the tide's going in, they vertically go up. So it pushes them a little bit further. When they're getting ready to go out, tide is going to ebb, they drop to the bottom and they'll hug the bottom, and it keeps them from being just taken away. And they also actually partition the estuary as you go offshore. Offshore, you tend to find more of the small babies, and as they get closer into the bay, they start growing and metamorphosing, and they settle down. Anyway, these estuaries are very productive in terms of fish production. And of course, you have birds and a lot of other organisms that feed on them. And here's just a typical life cycle you see here in the Gulf of Mexico. And again, other critters feed on them. These are typically found in different types of habitats. We have seagrasses beds, we have salt marshes, and we have mangroves too. and then just mud flats. So I'm not going to have time to go through everything, but what are some of the potential climate change effects? Again, I mentioned it earlier. It's not just heating, it's variability. You know, you got big switches in terms of, you know, temperature going really far up and then dropping really quick. You have changes in wind patterns. The wind we get along the coast, most of that's due to different, you know, 24-hour heating and cooling, where the water gets, you know, warmer than the air on land, and so it switches direction. We also have river discharges varying too, and that can be extremely variable. Here in Texas, we have had big droughts, and where a lot of our major rivers have dried up. A few years back, we were out doing some work, and there was whole streams that you walk down and you don't even hear nothing making noises, not even birds. And one time, I think I might have said this in past class, I was out and we were doing these studies for TCQ, and we were in this stream that was bone dry, just little puddles of water here and there. And it was back, I don't know, when we had 2 years back when we had a drought, and you didn't hear anything. I was just like it was creepy. Like, man, there's like nothing alive here. You didn't even see birds flying. Then all of a sudden we hear clump, 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 clump. Around the curve, around the bend of the river, here comes this old skinny horse, barely alive. I said, man, this is like out of a Western movie. People that live in the city don't know what a drought is, because you don't feel it. You know, you got your water out of your tap, but it just messes with the whole ecosystem. And again, there's all this stuff going on in the watershed as well. Any questions?
What's the best way to find those microbursts?
Or are you talking about in a stream? If you can get one of those little dip nets that you can sweep with, you know, and then like, you know, if you say you're in a riffle area, you know, shallow with a lot, you know, like a little mound, you can kick them, you know, and then have the net right downstream so things will float into it. That's a good way to do it. And you can use even seines like that, you know, like a regular, just roll it up, put it like that. They make them for invertebrates, a smaller mesh, but you can use a bigger mesh. So you'll just get bigger stuff.